Fibonacci. Oh, sorry, I didn't see that. Okay, so we're going to give this a go. This is hopefully going to be the first of many online lessons that I upload onto YouTube so that you guys can have a look. Without further delay, let's just get into it. This lesson is lesson 2. We're looking at modeling linear growth and decay. Now, the key word here is linear. What I would like you guys to try to do for this topic, for finance, for this whole topic, is to have something like this as your notes. Having a table really sets out this topic nice and easily, and you can see the differences between the types of questions that you can be asked. Now, in today's lesson, we're looking at both linear growth and linear decay. I've got a couple of pictures here. Let's look at them a bit bigger. So for linear growth, we've got something that changes over time, and it's changing each year that it changes, so 2011 to 2012, or each time period that it changes, we're getting the same amount of growth. It's changing by 100 each time, so you can see these points. If I go up here, this point, 2016 to 2017, also changes by 100. So that's what characterizes linear growth. Linear decay is similarly a change that stays constant, so that the change is staying the same. Here we're decreasing by 100. So we've got a decrease of 100. You can see here this would be at 900 because it's halfway between 800 and 1000. And if we go anywhere along this graph and look at any two dots that are consecutive, we can see that the changes are going to be the same. The change here is also 100. So this vertical change here. Linear growth and linear decay. Should be quite familiar to you guys by now. Let's look at what we did last lesson. Consider the recurrence relation below. A0 equals 2, an plus 1 equals 3, an plus 1. Now, you guys will pause the video, give this a go, and then come back, but I'm going to do the solutions right now. So pause it now and give it a go. All right, so our starting value is 2. So if we want to generate the sequence, we start with 2, because our starting value is 2. Our next value is going to use 2 and do 3an, which is 2. So 3 times 2 plus 1, which is 7. So to find the next value, we substitute 7 back into this formula. So 7, 3 times 7 plus 1 is 22. Now let's look at the options. We should see that we've ruled out all of them except this one, 2, 7, 22, so it has to be E. All right, now we want to model linear growth and decay using a recurrence relation. So for linear growth, our recurrence relation is Vn plus 1, as in the next value, is equal to Vn, which means the current value, plus whatever the change is. So in this case, we're calling the change D. This is where you guys should be going to your notes and putting in some notes that look something like this. Simple interest, V0 is the principal, which is also our starting value. And our rule is Vn plus 1 equals Vn plus D. So that's our rule. Now what is D? Depends on whether you're given a rate. So if you're given a rate, that's like 5%, 12%. If you're given a rate, then you'll do 5 or whatever the rate is divided by 100 times the principal. And that gives you the letter D. So what number you need to put in there. So let's write that into our notes. D is therefore R over 100 times V0. That is how much we're adding to the account every month or every time period. Here we've got years, but that could be months, weeks, days. It's a fixed time period. Let's look at some questions so we can see how to apply this. Anita invests $500 into her cooking career savings account. She earns $40 simple interest every year from Acorn Investments. So I think a really good habit to get into is underlining the numbers and assigning them what their variables are going to be. So in this case, $500, that is our principal. You don't have to write principal, but I'm just going to write it here. Another name for that is starting value. And $40 is going to be our D, so that's how much it's changing by each time. Now that makes it super easy to write a recurrence relation. Remember, recurrence relations always start with V0. So V0 equals 500, and then Vn plus 1. Recurrence relations also need a rule with Vn plus 1 on one side of the equal sign, and then on the other side, we need something that has Vn in it. Vn plus $40, because this is simple interest, so we're just adding $40 every year. So that's it for this question. Now, the information is the same. What will her balance be after 5 years? Well, again, V0 equals 500, Vn plus 1 equals Vn plus 40. Our starting value, let's just generate the sequence. So our starting value is 500, then our next value is 540, just 500 plus 40. Then we add another 40, 580, another 40, 620, then 660, and 700. And if we write, this is the starting value, so 0, 1, 2, 3, 4, 5. So after 5 years, so this is the starting value, after 5 years, 2, 3, 4, 5, we have $700 in the savings account. The last type of question is, what is the simple interest rate for this account? Remember, the simple interest rate is R, and our formula is R over 100 times V0 equals D. In this case, we're asked to find R. Now, here's a little bit of algebra, but if you just want to write down the formula, that's also fine. R is equal to 100 times D divided by V0. So 100 times how much it's changing by divided by V0, which in this case is 100 times 40 divided by 500, which is 8. So 8%. The interest rate is 8%, simple interest. And I was joking, that wasn't the last simple interest question, this is. Anita decides she isn't going to end up with enough money after the time she wants to invest. She needs to be at $2,000 after 5 years. The Acorn investment still provides $40 per year. What does Anita now need as her principal? Well, let's think about this. She needs to have $2,000 at the end of 5 years. So that means we're going to be going, we can even be starting here. There's a couple of ways to do this. We could start with 2,000 over here, and we can work backwards. And we're trying to find the starting value if we want to end at 2,000. So this will be 1960, this will be 1920, this will be 1880. So I'm just subtracting 40 each time. 1840, and finally 1800. Now, hopefully you guys remember how to do this in your CAS as well. We're just going to quickly do it. So remember, with your starting value, you just type the number, press enter, and then you enter what you want, what the recurrence relation rule is telling you to do. So in this case, it's telling me to subtract 40. So we want answer minus 40 each time. And so that's 1, 2, 3, 4, 5. So we are correct. 1800 is what is the value that you need to start with. Now remember, guys, this is a video. You can rewind and look at anything that I've been doing. Pause, slow it down, speed it up. I'm sure many of you would want to speed this up because I am a bit of a slow talker. So please do that. Use this video however you want. Now, we've looked at simple interest, which is our example for linear growth. Now, for linear decay in further maths, this means flat rate, or the example that we use in further maths is flat rate depreciation. All right, so let's go back to our notes. Right here, flat rate depreciation. Now, for flat rate depreciation, here is a bunch of text. You guys know how much I love bunches of text, so walls of text. There's a lot of information here. The key things are in bold, as in the key terms that you'll need. Depreciation is essentially where an item loses value over time. So if you buy a car brand new, you say you buy it for $20,000. As soon as the car leaves the showroom, it's already gone down in value. You can no longer sell that car for $20,000 because it's used. I think a lot of you will be familiar with that concept. As a car gets older and older, it loses more and more value. That process is called depreciation. The future value refers to the estimated value of an item at any given time. So if you ask for the future value of a car 3 years into the future, that's what it's referring to. How much will it be worth in 3 years? Scrap value refers to a time when an item has depreciated to the point where it will be sold or disposed of. So when it's at the end of its useful life. Now, there's many questions in further maths where it asks about scrap value, and it will give you a scrap value. When it's at the end of its useful life, it's said to be written off. It's just a term that we use. Flat rate depreciation and unit cost depreciation are examples of linear decay. So we only wrote down that one, but there's also unit cost, which we'll talk about a little bit too. Now, flat rate depreciation occurs when an item loses value at a constant rate. Constant amount, it's subtracted every time period. So what we're talking about with linear decay, the amount of change is the same each time period. You get a straight line. Unit cost depreciation occurs when an item loses value according to the amount of use rather than an age. So on the x-axis, you now have the amount of use rather than the time in years. So our model for flat rate depreciation, which is the first one that we're looking at, is this. So let's go back. V0 is now not principal, because principal is the amount of money that we put in. This is the initial value. Slight distinction, but all you need to know is whatever the starting value is, whatever you started with. So say you bought the car for $20,000, that's the initial value. Now Vn plus 1, we know all of our rules have Vn plus 1, and we've already given it away. It is a linear decay, which means that it's going to be looking like Vn minus some amount which stays the same. In this case, we're calling it D. All right, so that's our recurrence relation. And remember, D is equal to this thing. So we should be seeing some parallels between linear growth and linear decay. They're very similar. In fact, the only difference is really this minus sign rather than a plus sign here. So D is equal to that. And that's not any better, but let's just go on with it. For example, let's look at a recurrence relation example. Okay, let's look at this. A printing press is bought for $15,000 and depreciates by the flat rate method. Depreciation was 15% of the purchase price each year. Its useful life was 5 years. Okay, so there's a few things here. Let's annotate the question. So $15,000 is V0 because that's what we're starting with. Depreciation was 15%. That's R. Its useful life was 5 years. So at the end of 5 years, there should be no value left. Or that's the scrap value of the item. In this case, a printing press. Find the annual depreciation. So annual depreciation, this is asking for D, the letter D. We know D is equal to R over 100 times V0, which in this case is 15 over 100 times 15,000. Now, if you're not sure what I'm doing here, don't worry. I was going to try to do that in my head, but I'll use a calculator. 15 divided by 100 times 15,000. 2250. So our printing press is depreciating by $2,250 per year. Set up a recurrence relation to represent the depreciation. All right. Remember, recurrence relations have V0, and we know the V0 is 15,000, and recurrence relations also have Vn plus 1. We see that it's flat rate, so we know it's linear decay. Linear decay looks like Vn minus D. Now we already know what D is. We just calculated it. It's 2,250. And that's it for depreciation.